Hi, thank you for joining from wherever in the world you might be. What I will be speaking about today is very much aligned with our theme that AWS is highly focused on helping builders bring cloud connectivity and intelligence to the edge. I'm Richard Alberger, and what you will learn today is how to do cloud-driven continuous integration and continuous deployment from the cloud. Throughout the talk, I will be giving examples in the context of a real cloud, Amazon Web Services. So we won't be talking about anything fictional here. What you'll see today is an evolution of ideas that first started in some offices in Logroño, Spain, having a casual conversation with the staff at Digi International. As I learned more about embedded Linux, though, I really want to view embedded Linux from a cloud-first perspective, seeing how we can operationalize all embedded Linux delivery aspects from the cloud. I'm excited to be your speaker for this session today. I've had a few different roles at Amazon, but I have been doing embedded development and IoT evangelism for building solutions on top of AWS for the last several years. Although we're focused with some of the AWS cloud services for CI/CD today, the AWS cloud connectivity comes from the Meta AWS project. Meta AWS is the bit-bake layer for building and installing AWS device software to embedded Linux using the Yocto project and also automotive-grade Linux. First, I will show you a good overview of the typical IoT product lifecycle and how embedded Linux-related activities fit into that. Then I will go step by step through the roles in the lifecycle. These are the contributors and the consumers. Many times people call them actors, but they're not acting. We'll get a bit deeper into lifecycle artifacts from prototyping to development to maintenance. I'll cover it all. I'll also show you how you can capitalize on IoT device runtime behaviors and make purposeful changes for your customers that drive maintenance cycles and over-the-air updates. Really, what we're going through in these slides, I want you to realize the benefit of doing these things in the cloud. Think about the servers you would need to buy, the storage you would need to buy, and once you buy those things, you can't increase capacity quickly. You don't have the usual desired resiliency unless you spend a lot of money up front. And then there's a global reach you might need. So think about all those things, and now let's get started. As mentioned, we're first going to take a look at where CI/CD fits. Well, it's basically related to all the work where the rubber hits the road, right? Now, don't get upset when you first see this slide and say, oh, well, that's a waterfall process and no one does that anymore. Well, it does from this perspective, because having your IoT product idea and then decommissioning it are the backends where we have our newfangled agile processes there in the middle. At first, you have your IoT idea, what it is, how it's going to be awesome for your customers, how you're going to make money. Define the problem that it solves, right? You might even build a demo on a Raspberry Pi or something, and magically you get your project funded. But this is where the rubber really starts hitting the road. You hire people to build an awesome prototype where you can refine the rough edges of your idea. Then you need to do the hardware design and then go evaluation board hunting. And you know you'll be building a custom Linux distribution, so system engineers get their feet wet with board support packages from those semiconductor companies. Then you get to the point where you identify the processor, and then your new hardware engineers can do the hardware design. The system engineer gets to work defining the Linux device tree based on the hardware specification, and then defines the software packages to include into that distribution based on the application requirements. You do development builds and QA builds, and then your final manufacturing Linux distribution build. You ship your amazing IoT product. Now maintenance begins. As your user base grows, you need, you learn of cool enhancements, right? To make and uncover a few bugs that snuck into your code base. And that's where over-the updates come in. CI/CD is going to help you get updates out the door using a repeatable build process for a critical delivery process that you can't afford to have go wrong. And then, 5, 10, maybe 15 years later, your IoT product dies a lonely death. I know, it's sad, but really 5 to 15 years, it's a great run. So now, when you're in between the bookends on the previous slide, there's a lot of activity going on. For embedded Linux specifically, most of the source code is going to come from people outside your team. The term open source community can seem pretty nebulous, but it needs to be. These are folks contributing to open source software coming from all walks of life. Open Embedded is a project that reflects all these open source projects as software packages that go into the system driven by a scripting language and a tool called BitBake. Packages include the Linux kernel and systemd and web servers and Python. All the things you would expect from an operating system today. The semiconductor companies usually provide processor-specific drivers, kernel patches, and value-added tools. When we talked about the evaluation boards in the previous slide, they were usually, they will usually deliver the device tree and other configuration specific to the evaluation board there. Next comes your custom engineering. Your system engineers are going to define what your Linux distribution looks like and curate to a minimum set of software for your application in that distribution. Like mentioned previously, they take into account application requirements or dependencies and are many times responsible for the CI/CD system itself. Then you have your IoT application itself finally, right? After all of that, this is all of your application's secret sauce that needs to be installed on the target firmware. Then that gets all culminated to a software manufacturing process. This process is mostly a bunch of automation that takes the inputs from the suppliers and constructs them to outputs that can be consumed by folks later on in the process. We will be talking about that in a lot of detail in the slides coming up. But then we have outputs from this process and many consumers. At some point in the process, all outputs will be created. But let's start with what needs to be built in the beginning. The developers are likely to be developing the software for a processor target that doesn't match their development machine's processor architecture. The build system can output a software development kit to help these developers write and test code using a cross-compile environment. When they deliver code, the build system runs and delivers the firmware image to the developers as well. Of course, this will happen initially without the developer software, based on the system engineer's inputs. Remember, this is a SIPOC diagram that doesn't represent time, but at some point in the cycle, the same output, the software image, will go to contract manufacturers. Throughout the cycle, your QA team will be receiving a QA image that not only has your application code, but also includes the unit tests that need to be run when integrated with the hardware. Then, of course, is the most important consumer here, your customers. As you're surely aware, the customers don't get the initial product image directly. They get it as part of the finished product. What are we developing here? The system updates are being delivered to continuously improve the product across the life cycle. With that landscape in mind, let's dive deeper into these roles that can play throughout the SIPOC. The system engineers are there from the start and are considered the distribution maintainers. Like mentioned briefly before, they can also play the role of configuration or release engineer, where they are maintaining the process between the bookends that I talked about throughout the development and maintenance life cycles. Since they're responsible for the distribution definition, they also need to keep an eye on things like security patches from package dependencies, including the Linux kernel itself. The software engineers mostly participate in the development part of the cycle, but can deliver product enhancements during the maintenance phase. For sure, the velocity at which they might work can be a lot less in the maintenance phase. Many times the focus is on the application bug fixing and maybe small enhancements through the maintenance phase. Quality engineers will write test cases throughout the development phase and lean on the software development kit to write those cases. Usually there isn't much case development going on in the maintenance phase. Well, maybe if there's a feature enhancement in the maintenance that needs to be tested, but the activity would be limited to that. Throughout the maintenance phase, the test cases can be run automatically against hardware targets using tools like LabGrid. The resulting output is the QA image itself. Let's see how these outputs translate to actionable outcomes in the CI/CD process. Now, in the last slide, we went through what those rules produce as outputs, either directly or indirectly. But where do those outputs go? One of the outputs of the process is the production firmware image. Once that's made, it needs to be stored somewhere. A firmware image can be large. Nowadays, with ML toolchains, I've seen images as big as 4 gigabytes. Unless they're, well, usually they're less than a gigabyte though, right? But that's still pretty large. In the cloud, you would store that into object storage, right? A highly resilient and elastic cloud-based storage mechanism. And now once the image is stored and secured, you can distribute that image globally. For example, you can distribute your image to a contract manufacturer using a self-destructing URL that has a finite lifespan. Or your global developers and test labs can download it from there as well. Now, system updates patch the running system, right? When working with Yocto, you might know that you can do both block level and file level system updates. Block level is usually done with SW update or mender, which is effectively a firmware over-the-air update. You should have enough flash to do a fallback image though, right? Now with file level, this is kind of like using a package manager a little bit, kind of like Yum or RPM, but you don't need to install the whole package, right? If you're just patching one file. So for example, with SWUPD, you can micromanage what gets updated into bundles. It's just another kind of construct. OSTree is another popular one, but SWUPD is maintained by Intel for the Clear Linux distribution, right? So it's highly used. Now, like a firmware image, the system update needs to be staged and also be HTTP accessible to all of your IoT devices. And many times that can be all over the world. So how do we make that more available? Well, we can easily front the object storage with a content delivery network to increase the points of presence all across the world. That way, customers can lean on the CDN, or content delivery network, instead of a single download point, right? Which would be a single point of failure. The software development kit is the cross-compilation environment for internal or private consumers. It includes headers, object files, and it's built across, it builds cross-development tools. So developers don't need to build the entire distribution themselves. It helps them scale. So where do we stage the software development kit? We could stage it to object storage as well. The private consumers could have more permissive access to the cloud, and they can lean on more rich development tools. An artifact repository is a good way to store managed revisions or versions and allows developers to use those packages in a development environment natural way. So our last output and consumer here we're going to talk about is the QA engineer. These engineers will run labs and need to take the QA image and apply it to the hardware. They may need to apply the test image to maybe tens or hundreds of targets in the test lab. We really don't want to have to copy that test image down so many times. So we do want to store it locally. Once the image is local, you can use LabGrid agent. It's just a little piece of software that facilitates the transfer between a small machine and all your lab machines. So it transfers to the target device, its eMMC, or whatever storage it happens to have. Now, to do that, we see people implementing processes similar to rsync to get that image down to the edge. And they can get the image local, and then, well, there might be an easier way to do that using AWS. And I'll get to that case in just a few slides here in the reference implementation section that's coming right up. So let's see how we can piece all this together in the cloud now, like tangibly, like something that can really be executed on. Like I said before, I talked about the rubber hitting the road. This is where it really hits the road, where you have it implemented and the CI/CD process is running. But again, I kind of teased you. Before we dive into the CI/CD specifics, I want to focus on the maintenance cycle for a moment, because I didn't really talk a lot about that, like what drives the maintenance cycle. How do you continuously get feedback from your customers, harvest the feedback, make implementation decisions, and then get those enhancements back out to customers in the system update process? Well, it's no different than what I show folks at reInvent 2019. When your IoT devices are running, you're communicating with the central IoT service, right? Most of that data will be application data, data you can't harvest for privacy reasons, right? But part of that can be application behavior telematics. For example, devices in the field are behaving in unexpected ways due to environmental conditions that you haven't been able to test during your test cycle. Now, some of that data can alert you about security issues, which you can take action on as well. But other behaviors might be harder to analyze abstractly and requires algorithms that reflect your secret sauce. You can build and refine those algorithms to make decisions about that data. For things that don't require machine learning analysis, you can feed the data into AWS IoT Analytics, which gives you a refined data set for making informed analytical decisions. Those decisions get realized as software requirements that can drive those code changes. The reflection of those changes can then trigger events down to your device, which could then be as simple as a volatile file change, like a modifiable configuration file, or it could trigger the SW update process to start the entire system update process. In our case, IoT device management wouldn't be sending the image, but it would be sending a reference to the image where the SW update process can take over. Let's see how the CI/CD process facilitates this. We're going to just wrap up the technical part of the conversation in this deck with the tangible flow of doing this in the AWS cloud. I'm going to be talking about a lot of different cloud services here, but I hope that in context, you will have an idea of what the name, well, you can actually bridge the name with the actual purpose of the service, right? All along the open source community, has been contributing to upstream packages like the kernel. Now, without any contribution from your development team, the system engineers will need to build images for your evaluation boards. Just for brevity here, we're missing the input from the semiconductor companies for the baseline BSP though. The build system has a really straightforward project to set up. It uses a service called AWS Code Build, which provides a container-driven build process. And once the build completes, the firmware image gets stored in Amazon S3, the object storage I spoke about earlier. Then we need to get the images down to the edge so we can apply them to hardware. Another storage mechanism for our customers is AWS Storage Gateway. It synchronizes Amazon S3 buckets in the cloud down to the edge. Okay, good. That's great for prototyping. What's next? Well, your system engineers, software engineers, and QA engineers will start committing code. You can use GitHub, no problem. But if you need to apply additional role-based security, you can use AWS Code Commit, which uses Git under the covers as well. Now, we have several processes that need to be kicked off in parallel: the basic image, the QA image, and the SDK. Again, we stage the firmware to the S3 bucket and then store the QA image to another bucket, because remember, this has more private settings for private consumers, like your QA team. Then the SDK can be staged either to S3 or to AWS Code Artifact. It's your choice what you would like to use. In this case, for simplicity, I'm just using a single bucket. Depending on your use case, though, and desired internal development team experience, you might choose AWS Code Artifact. And then the new firmware image syncs to your Office, along with your QA image and along with your software development kit. And now, as the suppliers on the left, the system engineer, the software engineer, the QA engineer, make commits to those repositories, it can trigger fresh builds, delivering fresh firmware, and the SDKs down to the edge so they can do additional development work. This is the power of CI/CD. This is why you want the constant feedback loop mechanism and the eventing of the builds to drive those additional changes. Now, when the development cycle completes, though, you can send the pre-signed URL to your contract manufacturer. A pre-signed URL is an S3 feature that is like a pass to get a file for a limited amount of time. Then CloudFront will go and fetch the image from the S3 bucket after the signature gets verified. After downloading, the contract manufacturer can then stage the image for the manufacturing process. Okay, so we built our products and sent them to customers. Now the devices are interacting with the AWS cloud in some way. Remember the slide a few moments ago with the continuous improvement cycle? This is where it fits in. Once the device gets a signal from AWS IoT device management, then the device can act according to the software update process chosen by you. In the reference implementation, I use this SW update. So CloudFront has a lot of good points of presence worldwide and uses S3 as a source of truth. That's Amazon S3. When a user hits the URL for the first time, CloudFront will cache the image at the point of presence, making your device firmware download potentially faster, since it could be closer to additional devices. Now, again, the maintenance process is critical, not a one-off, right? So once the cycle runs through again, then the devices can be notified once again and from IoT device management and be updated once again throughout all the future maintenance subcycles. Okay, so I am really happy that you're still hanging on through what that whirlwind tour of Embedded Linux CI/CD was doing in the cloud. You are able to understand how Embedded Linux CI/CD fits into the product lifecycle, specifically for development and maintenance. You really need to be doing this in the cloud today because customers expect global operations. The easiest way to achieve that is with the cloud. And why not? It's so easy to get elastic results. And as your business grows, so can your infrastructure needs without physically buying new hardware. Okay, well, that's all. And please check out our other sessions at Embedded World. Thank you.